Hey everyone, this is Dr. Walker. This is video 229 and it's called Resistance and Resistors. Let's start off this one with a question. How is this possible? The night light turns off automatically during the day. So I don't expect anyone to know about this, but I'll give you a hint. It has to do with the resistance of the night light. There's a sensor that has a resistor and it's going to be affected with the daylight. So no, I'm not giving you too much, but if you have any thoughts, please feel free to put them in the comments below. So this leads us to resistance, which is a measure of how easily charges pass through the material. All materials have resistance, so that means that they are inhibiting the flow of charges. You see a light bulb here, you see the filament in the bulb, there's resistance there when the charges go through. The charges collide with all the atoms here and cause it to glow and light up. So there's definitely resistance in every single material. On the left here, bottom left, we have pictures of resistors, which are actually designed to offer a specific amount of resistance that you can tell the amount of resistance by looking at the color codes on the resistor. And then finally, I have a picture of a little circuit, and we can see that we show anything that has resistance, we'll show it as a resistor in our circuit, and it's going to be shown with these little jagged lines. So the other thing about resistance is that the units are ohms. So we have this Greek letter omega. And as I mentioned, all materials resist current flow to some degree. So it's a matter of how much resistance does each material have. When we're dealing with circuits and we're talking about the wires in the circuit, in this class, we're going to ignore the resistance of the actual wires, because otherwise it would make life way too complicated. And the wires are designed to have very little resistance anyway. So we're just going to be considering the resistance of cylindrical resistors that are specifically put in circuits to have a certain amount of resistance. So which factors affect an object's resistance? The first picture here shows that you have a thick wire versus a thin one. So the cross-sectional area is going to affect the resistance. So if you think about this wire here, the charges are flowing through this circular cross-sectional area. That is a factor that affects the resistance. Now again, I said we're going to ignore the resistance of wires when we're dealing with circuits, but this picture has wires just to show the different factors that affect the resistance. And then what we also see here is that this wire has a different length than this one. So the length of the wire also affects the resistance. And finally, our materials can be made out of anything, right? So copper and iron, they're going to have a different amount of resistance. You can see in the picture on the bottom left here that there's more current flowing through the copper and less current flowing through the iron. This means that the iron has a higher resistance and the copper has less resistance. Likewise with the previous picture, when you have a big area, you have more current, which means less resistance. When you have a bigger length, then you have less current. That means that the resistance is higher, right? So resistance and current are inversely related. If resistance goes up, then current goes down, and vice versa. Let's take a quick look at this applet. It's just for visualization purposes. I have it open here. It's the FET resistance applet. So it shows this equation that we're going to see on the next page, but this is for a cylindrical resistor. It's showing that the resistance of the resistor depends on rho, which is called a resistivity, and then L, the length, and A, which is the area. So the resistivity is just a property of the material. Every different material has a different resistivity. You can see when I slide this bar here, if I decrease resistivity, the resistance goes down. If I increase the resistivity, then the resistance goes up. What you also see in the picture, as I decrease the resistivity, there's less little points here in this resistor. As I increase the resistivity, there's more points. So the points here are indicating the impurities in the material that are indicating the resistivity and resistance. When there's a whole bunch more impurities, then there's going to be more resistance. They're going to impede the flow of the charges that are trying to go through. Let's look at how the length affects the resistance. So you can see as the length increases, the resistance increases, and vice versa. The length decreases, the resistance decreases. We can see again from this picture that if you have a bigger length, then you just have more impurities. So there's more impedance to the flow of charge. So it makes sense that they're directly related. And then the area, you can see as you increase the area, then the resistance decreases. As you decrease the area, the resistance increases. So you can see that when charges are trying to flow through, if you have a bigger area, then there is just more room for the charges to flow. So bigger area, less resistance. So I just wanted to go ahead and show that, and let's go back to the notes here. So this is the equation that we just saw. The resistance depends on the resistivity, rho, the length L, and the area A. So hopefully it makes sense how all of these factors affect the resistance of the resistor. Let's go ahead and do this question here. Suppose an electric wire is replaced with one that has both its length and radius doubled. How does the resistance of the second wire compare to the resistance of the first wire? So the first thing is to realize that we're changing one or more variables, so we need to figure out what is the related equation. We're talking about resistance. Resistance equals resistivity times length over area. So we know that changing the length will affect the resistance. What about changing the radius? The radius doesn't appear to be in the equation, but it is though, because this is the cross-sectional area here. This is a circle. A circle has an area which is pi r squared. Pi r squared, I'll use a little r so we don't confuse it with resistance. Pi r squared is the area of your circle, of your cross-sectional area here. So if you double the area, take a look. If you double the radius, take a look, you can see that you now have 4 pi r squared when you double the radius. So this is A1, then this is A2 here. So A2 has 4 times the area because we doubled the radius. So back to our resistance equation. The resistivity is not changing. The length is doubling, so we're going to have 2L for R2 here. And then for the area, we said we're going to have 4 times the area when we double the radius. And now we simplify and we get a factor of 1/2 in the front. 1/2 rho L over A. So we can see that the new resistance is 1/2 of the old resistance, R1, which was the old resistance. So that is our answer. And that's it for this video. Be sure to look at the guided example for this video as well.